Okay, so I want to go over that free response problem because it kind of brings together a few ideas from the section on rotational motion, and because it's pretty similar to at least one of the questions that's going to show up on the AP exam. So in these types of questions, there's not actually a whole lot of computational work that you have to do. It's more justification through, talking about the principles and then, occasional reference to equations, but not necessarily with plugging in any numbers in. So let's take a look. They show sort of three stages of a diver. The diver jumps from the platform, and their body is relatively straight, and they tuck into a ball and rotate, in the middle portion of their dive, and they straighten back out right before they hit the water. So in part A, they ask you to explain why the diver's angular speed increases between figure 1 and figure 2, but then decreases between figure 2 and figure 3. So the first thing that kind of everything else in your explanation should hinge on is the idea that angular momentum is conserved. Okay, so just like linear momentum is generally conserved, angular momentum is also conserved. It stays the same. So you want to start with some kind of statement of that, a statement of conservation. So you could say angular momentum is a conserved quantity. Okay, then you want to talk about the actual formula for angular momentum. So angular momentum, it's represented as L, okay? And that equals I times omega. Okay, so L, this is angular. I is what's called the moment of inertia. And omega is the angular velocity. So this equation is very much analogous to the equation for linear momentum. So linear momentum, we have P equals mv. Here we have just those analogous angular quantities. So P is linear momentum, L is angular momentum, I is moment of inertia, m is mass, and omega is angular velocity, v is linear velocity. Because L depends only on I and omega, as one quantity increases, the other must decrease. Okay, so this is kind of the next logical step from your statement of conservation. So angular momentum is conserved, and because it only depends on these two quantities, and they're just multiplied together, as one quantity increases, the other quantity must kind of decrease in compensation. And then what we need to discuss is how the moment of inertia of the diver changes through the course of the dive, okay? What is moment of inertia? It is basically a measure of how spread out an object's mass is. If we look at these sort of three positions that the diver takes, the diver's mass is basically spread out in the same way in figure 1 and in figure 3, right? The diver's sort of stretched out as far as possible. In figure 2, the diver is compressed, okay? So in general, the average distance of the diver's mass from the center of mass. The center of mass is going to be somewhere around here. The average distance of the mass from the center of mass is going to be larger in figure 1 and in figure 3, and it's going to be smaller in figure 2. And as the average distance of that mass from the center of mass, center of rotation, increases, then the moment of inertia also increases, okay? So you could say something like I is greater in figure 1 and 3 than in figure 2, because the diver's mass from okay, because the average distance of the diver's mass from the center of rotation is greater. You don't necessarily need to go deep into the underlying math, because that's sort of beyond the scope of AP Physics 1. But you know, if you wanted to, you could think of figure 1 and figure 3. The diver's shape being similar to maybe like an oval-shaped disc or a rectangle, and in figure 2 being more similar to a sphere. And if you look at the formulas for moment of inertia of those two things, it's pretty clear to see that because of this much greater distance from the center of mass in this figure as compared to this figure, you're going to have a greater moment of inertia here versus here. But you don't really need to get too deep into the underlying mass. Therefore, so you could say, therefore, omega, which is that angular speed or angular velocity, must be greatest in figure 2. And will increase from 1 to 2 and decrease from figure 2 to figure 3. Okay, and so that's really all you need to say about that, about part A. So because this whole quantity of angular momentum is conserved, if you have moment of inertia going down, then angular velocity needs to go up, and vice versa. And so we see moment of inertia going down from figure 1 to figure 2, but then going back up from figure 2 to figure 3. Okay. And then if we look at the, sorry, let me just scroll through here. If we look at the question in part B, they ask, is the rotational kinetic energy of the athlete in figure 2 greater than, less than, or equal to the rotational kinetic energy of the athlete in figure 1? And they want you to briefly explain your answer. So again, what you want to do to start is kind of appeal to an equation. So you could say rotational kinetic energy is equal to 1/2 I omega squared. Okay, so again, this is very much analogous to linear kinetic energy. Linear kinetic energy is, of course, 1/2 mv squared. Here we have the corresponding rotational quantities. So we have moment of inertia instead of mass, and we have angular velocity instead of linear velocity. We can rearrange this equation, okay? So we could say, by simple algebra, we can write okay, so we simply take this omega squared and turn it into omega times omega, okay? And what's useful about this is, if we look at this quantity here, I omega, okay, we can say because L, that angular momentum, equals I omega, we can say that rotational kinetic energy equals 1/2 L omega, okay? Because L is conserved, okay, as we talked about in part A, it is constant, okay? So we don't know necessarily what the angular momentum is because we're not specifically told what the mass of the diver is or what the moment of inertia or what the angular speed is at any point. But we do know that it's constant, so it's as much a constant as this 1/2 is a constant. So the only thing in this equation for rotational kinetic energy that changes is omega, okay? Because omega is the only variable quantity, okay, because omega is the only variable quantity in this equation, the rotational kinetic energy is greatest when the angular velocity is greatest. And then you could say, as discussed in part A, omega is greatest in figure 2. So you can say that the rotational kinetic energy in figure 2 is greater than the rotational kinetic energy in figure 1. And that's, again, really all you need to say there. So hopefully this was helpful. A kind of different type of problem, maybe than we've done in the textbook, but this is one of the styles of problems that you might see on the exam.